Imagine a simple scene. An egg sits on a kitchen counter. It is a perfect, unbroken oval. Suddenly, it rolls off the edge. It falls through the air for a brief moment. Then it hits the floor. The shell shatters into a dozen pieces. Clear egg white spills out. Bright yellow yolk spills out. A messy puddle forms. We have all seen something like this happen. It's an ordinary event in daily life. We understand what happened. Gravity pulled the egg down. The impact with the hard floor caused it to break. Nothing about this is surprising. We would not give it a second thought. Now, let's imagine a different scene. Imagine watching a video of this event. But this time, the video is played in reverse. What would you see? A messy puddle of yolk and shell on the floor. The pieces suddenly start to move. Pieces fly up from the floor. Pieces join together in mid-air. The liquid yolk and white flow back into the reforming shell. Shell pieces perfectly seal together. The now perfect egg leaps upward from the floor. It lands gently back on the kitchen counter, whole and unbroken. This reversed movie seems utterly impossible. It feels like magic or a cheap special effect. It is absurd. We know instinctively this never happens. Broken things do not spontaneously unbreak. Scrambled eggs do not unscramble into shells. Milk is poured. Coffee is poured. Once stirred together, they never separate on their own. This observation points to a profound truth. The world has a direction. Events unfold in a particular order. The past is different from the future. We can remember the past, not the future. This is the arrow of time. It always points in one direction, forward. But here is the deep puzzle physicists wrestle with. Why? Why does time have this one-way street? When we look at the fundamental laws of physics that govern the universe, the laws that describe how atoms and particles interact, we find something strange. Most of these laws do not care about the direction of time. They are time-symmetric. A movie of two particles colliding looks just as valid played forward or in reverse. So, if microscopic rules are reversible, why is the macroscopic world irreversible? This is the central mystery we will explore. We will embark on a journey from a simple broken egg to the very beginning of the universe itself. Our journey will take us deep into the heart of physics. We will need to understand some key ideas. One of the most important is something called entropy. You might have heard it described as a measure of disorder or messiness. A broken egg on the floor is in a state of high entropy. A whole egg on the counter is in a state of low entropy. The universe seems to follow a rule. Entropy always increases. This rule is the second law of thermodynamics. It's why rooms get messy. It's why ice cubes melt in a warm drink. It's why eggs break, but never unbreak. We will not stop there. To truly grasp why entropy increases, we must dive into the work of Ludwig Boltzmann. He reframed entropy with probability and statistics. Boltzmann showed there are far more ways for an egg to be broken than whole. The universe moves from less likely arrangements to more likely ones. Physics would allow the reversed movie of an egg reassembling, but the odds are astronomically small, longer than the age of the universe. This raises a bigger question. If entropy increases, the universe must have started at very low entropy. It began in a highly ordered, very special condition. Why? Why was the early universe so orderly? This takes us into cosmology, the study of the entire universe. We must look back almost 14 billion years to the Big Bang. The initial conditions hold the ultimate secret to time's arrow. My task is to be your guide. I will show how these ideas connect. A broken egg, the concept of entropy, the statistics of particles, the history of the cosmos. We will see that time's one-way flow is a consequence of the universe's story. It begins with a profound mystery, the neat, tidy state of the cosmos at birth. Let us begin our journey from this everyday puzzle to its cosmic origins, from clarity to a deeper understanding of the river of time. Let's start with a concept that sounds complicated but is actually very familiar. Entropy. At its heart, entropy is just a way of measuring disorder, randomness, messiness. Imagine your bedroom. When it is perfectly clean and tidy, everything is in its proper place. Your books are stacked neatly on the shelf. Your clothes are folded in the drawers. This is a state of low entropy. It is highly ordered and specific. There are only a few ways for your room to be perfectly tidy. Each item has one and only one correct location. It takes effort and energy to maintain this ordered state. Now think about what happens over the course of a week. You pull out a few books and leave them on your desk. You try on a few outfits and toss them on a chair. Papers accumulate. A cup is left on the nightstand. The room gets messy. This messy state is a state of high entropy. It is disordered and random. What is most important is that there are vastly more ways for your room to be messy than for it to be tidy. The book could be on the floor, under the bed, on the desk. The clothes could be in a pile here, a heap there. The number of possible messy arrangements is enormous compared to the single tidy arrangement. This tendency to move from order to disorder is not just about bedrooms, it is a fundamental principle of the universe. Think of two different colors of paint, say blue and white. You can start with a jar that has a neat layer of white paint on the bottom and a neat layer of blue paint on top. This is a low entropy, ordered state. Now you stir them together. The paints mix, creating a uniform light blue color. This is a high entropy, disordered state. The individual blue and white paint molecules are now randomly distributed throughout the mixture. You can stir for hours, days, or years. The paint will never spontaneously unmix back into two separate layers. This is because, just like with the messy room, there are countless ways for the paint molecules to be mixed together. There are trillions upon trillions of arrangements that look like a uniform light blue. However, there's only one way for them to be perfectly separated into two distinct layers. The universe, left to its own devices, naturally progresses from these special, ordered states to the much more numerous, generic, disordered states. This natural slide from order to disorder is what the concept of entropy captures. It's not a mysterious force. It's just a statement about the overwhelming number of ways things can be messy compared to the few ways they can be neat. This natural slide towards messiness is so reliable that it has been codified into a law of physics. It is called the second law of thermodynamics. The second law states that the total entropy of an isolated system can never decrease over time. An isolated system, a system that does not exchange energy or matter with its surroundings. In simpler terms, things get messier. A clean room left to itself will get dusty and disorganized. A hot cup of coffee will cool down, spreading its heat energy randomly into the surrounding air. The second law explains why the movie of the egg unbreaking itself seems so wrong. An unbroken egg is a low entropy system. A shattered egg is a high entropy system. The second law says you go from low to high, not the other way around. But calling it a law can be a bit misleading. It is not like the law of gravity, which dictates a precise force between two objects. The second law is fundamentally a law of statistics and probability. It's about what is likely to happen versus what is unlikely. The universe isn't forcing the egg to break and stay broken. The broken state is overwhelmingly more probable than the whole state. Think about the air in the room you're in right now. The air molecules are spread out more or less evenly, a high entropy state. Is it possible for all the air molecules to rush into one corner, leaving a vacuum elsewhere? According to the fundamental laws of motion for each molecule, yes. Each molecule is a tiny particle bouncing around. There's no rule preventing them all from bouncing the same way at once. But the probability is mind-bogglingly small, practically zero. You'd have to wait a time vastly longer than the history of the universe for it to happen. The second law is simply saying systems evolve toward their most probable configuration. So the second law is better understood as the law of increasing likelihood. Systems don't seek out disorder for its own sake. They evolve into states with the highest number of possible arrangements. A shuffled deck of cards is a great example. A new deck arrives in a specific ordered sequence, low entropy. After you shuffle, it becomes randomly ordered, high entropy. Is it possible to shuffle it back to the new deck order? Yes, but it's incredibly unlikely. There's only one new deck order, but about 80 unvigintillion possible shuffled orders, and 8 followed by 67 zeros. The second law just says you'll end up in one of the many, not the one of the few. We have followed the trail of time's arrow from a broken egg to the statistical world of atoms. Ludwig Boltzmann showed us that the second law of thermodynamics, the law of ever-increasing entropy, is a matter of probability. Systems move from ordered, improbable states to disordered, probable ones. This explains why eggs break and never unbreak. But in doing so, it introduces a deeper, more profound question. If the universe as a whole is subject to the second law, then it too must be moving from a state of lower entropy to higher entropy. This means that in the distant past, the universe must have been in a state of incredibly low entropy. It must have started in a highly ordered, special, and fantastically improbable condition. This is the ultimate why behind the arrow of time. The fact that you can remember yesterday but not tomorrow is a direct consequence of the universe's initial state. The reason coffee and milk mix but never unmix, the reason we are born, grow old, and die, is because the universe itself is on a one-way journey from order to disorder. All the small arrows of time we see around us, in chemistry, in biology, in our own lives, all point in the same direction because they are inherited from one great cosmic arrow of time. This master arrow was set at the very beginning, at the moment of the Big Bang, almost 14 billion years ago. Our entire cosmic history is the story of the universe slowly, methodically, and relentlessly using up its initial supply of order. So, the mystery of time's arrow has now transformed into a cosmological mystery. Why were the initial conditions of the universe so special? Why did it start in this low entropy configuration? This is not a question that can be answered by studying eggs or gases in a box. This question forces us to become cosmologists, to study the origin, evolution, and ultimate fate of the entire universe. We must journey back in time, using our telescopes as time machines to observe the faint echoes of the Big Bang. The answer to why time flows forward in your kitchen lies in the state of the cosmos billions of years ago. This is what physicists call the past hypothesis. It is the postulate, the assumption, that the universe began in a state of very low entropy. Without this hypothesis, Boltzmann's statistical explanation for the second law falls apart. Loschmidt's paradox would return, as there would be no reason to assume systems should start in an ordered state. The fact that the past is different from the future is not something that can be derived from the laws of physics alone. It must be put in as a boundary condition. It is a fundamental feature of our specific universe. Our task now is to understand what this low entropy beginning actually looked like and to ask why it was that way. So that's where the deepest questions lie. When we think of low entropy, we usually think of something ordered and structured, a perfect crystal, a tidy room. When we think of high entropy, we think of something messy and uniform, a gas filling a room, dye mixed in water. So, when we imagine the early universe in a state of low entropy, we might instinctively picture something complex and structured. But this is where we have to be very careful. When we are talking about the universe as a whole, we have to account for a force we have mostly ignored until now: gravity. Gravity changes everything. In a gravitational system, uniformity is not the state of high entropy. Clumpiness is. Let's first look at what the early universe was actually like. Our best evidence comes from observing the cosmic microwave background, the faint afterglow of the Big Bang, a snapshot of the universe when it was only about 380,000 years old. What this picture reveals is astonishing. The early universe was incredibly smooth and uniform. The matter and energy were distributed with almost perfect evenness across the entire cosmos. The temperature of the CMB is the same in all directions to an accuracy of 1 part in 100,000. It was a hot, dense, featureless soup of particles and radiation. No galaxies, no stars, no planets, no structure. This extreme smoothness is, from a gravitational perspective, a state of remarkably low entropy. Think about a collection of gas molecules in space. If they are spread out uniformly, gravity has not yet had a chance to do its work. The system is orderly and featureless. The gravitational potential energy is high but not yet realized. This is an unstable, improbable configuration. Given the slightest chance, gravity will begin to pull the particles together. Tiny, random fluctuations in density will grow. Regions that are slightly denser will attract more matter, becoming even denser. The uniform soup will curdle and collapse into clumps. So the smooth, hot, dense state of the early universe that we observe in the cosmic microwave background is precisely the low entropy initial condition that the second law of thermodynamics requires. It is the cosmic equivalent of an unbroken egg. It is a universe full of potential, a universe that has not yet begun to break under the influence of gravity. The story of the last 13.8 billion years is the story of gravity taking this smooth, low-entropy state and slowly pulling it into the clumpy, structured, high-entropy state we see around us today. The arrow of time for the cosmos is the arrow of gravitational collapse. The leading idea among cosmologists is cosmic inflation. In the first fraction of a second after the Big Bang, the universe underwent astonishingly rapid, exponential expansion. It grew from a size smaller than a proton to a size larger than a grapefruit in a tiny fraction of a second. Inflation would have stretched out any initial wrinkles or clumpiness, flattening space-time. Inflation also explains the tiny fluctuations, the 1 part in 100,000 variations, that seeded cosmic structure. During inflation, microscopic quantum fluctuations were stretched to astronomical sizes and became slight density differences in the early universe. However, inflation does not fully solve the ultimate past hypothesis puzzle. The honest answer: we do not yet know. Our journey to understand time's one-way street has taken us from the kitchen to the edge of the cosmos and the dawn of time itself. We have a compelling story. The second law of thermodynamics is a statistical law. The arrow of time it defines is a consequence of the universe evolving from an improbable, ordered past toward a more probable, disordered future. But the story is not finished. The ultimate why the universe started in this state at all, remains one of the deepest and most challenging questions in all of science. The mystery of time's arrow is not just a scientific curiosity. It touches upon our most fundamental experiences, our sense of cause and effect, our ability to remember the past and plan for the future, the very narrative structure of our lives, all depend on it. Every ticking clock, every memory formed, every choice we make is an echo of that primordial, low-entropy state from 13.8 billion years ago. The journey from a special past to a generic future is not just the story of the cosmos. It is our story too. The journey continues.